As we continue talking about limits of functions, I'd like to go back to the definition of a one-sided limit. We defined this earlier in this playlist, but when we look at a one-sided limit, we're looking at, for instance, this function here, and if we're looking at a limit at this number x equals 1, we may want to look only at the limit as we go to x equals 1 from numbers that are larger than 1. And in that case, we're looking at the limit x goes to 1 plus of this function, right? This is our function f of x. And so we can define a one-sided limit as usual as the value of the function as we get closer and closer to the specified variable. Now, we can also have a limit from the other side, right? We can look at the limit as we go to 1 from below, from the numbers that are less than 1. And we did say that if the limit from below is equal to the limit from above, then we know that we actually have a limit that exists. If they're not equal, we can't say that we have a limit to the function at that point. So that was a quick review, and if you somehow don't remember this, go back to the earlier video. So now that we sort of had this little reminder, I'd like to focus in on the main subject of this video, which is using the limit rules and one-sided limits to look at functions that include the absolute value. And as a reminder, the absolute value, say of x, equals x if x is larger or equal to 0, or it equals negative x when x is a negative number. So if x is negative 5, the absolute value is 5. We're basically saying we're looking at the size of the number and ignoring its sign. And it's interesting to look at this function when it actually goes through 0. So if this is the graph of absolute value of x, well, for x equals 0, we have 0. For x equals 1, we get 1. X equals 2, we have 2, and so on. So we have a straight line with a slope of 1 for the positive numbers. But if we look at x equals negative 1, well, for negative 1, the absolute value is plus 1, right? Because we're only looking at the size of the number, not the sign. And for negative 2, we similarly have positive 2. And so this is the shape of the absolute value function. And this shouldn't be new. But the point here is that now we want to look at the limit of absolute value x as x goes to 0. And we can ask ourselves what that's equal to. Now, here, because the function behaves differently at positive and negative numbers, we might expect that there might be some strange behavior at x equals 0. So we can look at the one-sided limits of this function as we go to 0. So what is the limit x goes to 0 from the negative numbers of absolute value x? Well, for negative numbers, remember, absolute value is just minus x or negative x. So we're looking at the limit as x goes to 0 from the negative numbers of just negative x, because at this point, for these numbers here, for x less than 0, that is the value of the function, and this is an easy function to take a limit for, right? It's a simple function. We're going to 0, so it just is equal to 0. We can actually substitute. What happens on the other side when we're going in this direction from the large x, or from the positive x to 0? Well, in this case, the absolute value is just equal to x right there. So we get the limit for x as x goes to 0 from above of x. And again, that's just equal to 0. So in this case, the limit x goes to 0 negative of absolute value x equals 0. And so does the limit from above, right? And so we can say that the limit x goes to 0, x, absolute value x, is equal to 0. And this is because the two limits, the two one-sided limits, were equal. So this is a nice example where we do take the two one-sided limits and we simplify our absolute value function, and we do get a limit at x equals 0. So obviously that's not the only example we're going to look at, because we're going to try to look at an example where things are not as simple. And our second example is f of x equals x, absolute value of x, divide by x. Okay, so in this case now we have a slightly more complex situation. Now, if we take the limit f of x as x goes to 0, both plus and minus, maybe we can just look at limit of the absolute value of x divided by the limit of x as x goes to 0, right? We know what the limit is here, and we know this limit too. The problem here is now that we're dividing by 0, right? The limit of x as x goes to 0 is 0. And so we have to be a little bit careful. So what we're going to do is we're going to, again, look at the one-sided limits and see if we can get the right values. So let's look at the limit of f of x as x goes to 0 from above. In this case, right, we're looking at the limit, x goes to 0 from above, of absolute value of x divide by x. In this case, we're looking at x's that are larger than 0. So they're positive, so the absolute value of x is just x. So we're looking at the limit, x goes to 0 from above, of x divided by x. Let's simplify that. That's just the limit of x goes to 0 from above of the number 1, right? X divided by x is just 1, and so our limit is just 1. So this is the limit from above. Okay. Now, what happens when we look at the limit from below? Limit f of x as x goes to 0 from below equals the limit of x goes to 0 from below of absolute value x divided by x. Okay, now in this case, we're looking at x's that are less than 0. So our absolute value should take on the opposite sign of x. And so we have the limit as x goes to 0 from below of negative x divided by x. Again, we simplify. The limit here of x goes to 0 from below is the limit of just negative 1. And again, because this is a constant, we can just write this as negative 1. So the limit from below equals negative 1, which does not equal positive 1, which is the limit x goes to 0 from above, right, of this function f of x. Okay, and in this case, we do not have a limit at x equals 0. We only have the one-sided limits, and this actually makes sense, right? If we want to draw this function now, if we go to large x's, we have the absolute value of x divided by x, which is equal to x over x when x is equal is larger than 0, which is just equal to 1. So we have just 1 right here, but that not at 0. And then for x's that are less than 0, we have absolute value over x equals -1. And so we're looking at this function here, right? But we do not include the point that hits x equals 0. So very clearly the limit here will go to 1, the limit here will go to -1, and we do not have a single limit at x equals 0. So this is a reminder of how to use the rules that we also, for the limits, we always have to be careful. First of all, we have to make sure that we don't take a limit and end up dividing by 0. We have to make sure that a limit actually exists, and we see that in some cases, even when using the rules, we have to reach the conclusion that a single limit does not exist at a certain point.